Introduction, and it's great to be here. This is actually my first time to Duke, and we've been blessed with lovely weather, which is really wonderful. So I'm going to talk today about an emerging concept that has a lot of momentum called generalist robot policies. And I'm curious, actually, I'd like to do a real quick poll before I jump in. How many of you are familiar with a VLA? How many of you have heard that acronym VLA? Go ahead and raise your hand if you have. Vision Language Action Policy. Good. I'm glad a lot of you have. How many of you have ever worked with a VLA personally? Like downloaded a Pi Zero policy and played with it, or OpenVLA? Okay. Put you on a couple. Good. Okay, that's kind of what I expected. I'm really glad. So this talk is trying to answer a question that is basically a scientific question posed about the current state of generalist robot policies, and specifically I mean VLAs, which is how general are they really? The claim is that they're meant to be quite general, and you type in a command and the robot will do whatever you ask it to do. And maybe you can tell by the little hint of skepticism in the title that that's not quite where we are in the state of the art. At the moment, generalist policies, I would contend, are quite far from this kind of ideal vision of you just tell the robot what you want it to do and it does it. That's not to say that they're not interesting or promising. They're super interesting and super promising. That's the whole reason I'm giving this talk. But it's important as scientists to understand what the state of the art is and understand where the opportunities lie. So I think the best example of the VLA is produced by this company called Physical Intelligence, Pi, which was a startup that emerged about 2 years ago. It spun out of a very active team at Google Robotics, and also led by a professor at Stanford, Chelsea Finn, and a professor at Berkeley, Sergey Levine. These are both very famous people. You guys have probably heard of them. And these folks, together with their collaborators at Google Robotics, developed this VLA concept, did all the early work in this concept, and then started the company 2 years ago. And then in this company, which is called Pi, Physical Intelligence, they have trained some models, and they've released the weights of these models to the academic community and the community at large, to be able to experiment and grow research in this area. And you can see, along with the original model that they released open source, they have this demo video, which is like amazing. If you've worked in robotics, this is breathtaking. To see a robot fold your laundry is like, whoa, that's okay. It was like, how do they even do this? There's no SLAM, there's no localization, there's no state estimation. There's no planning. There's a feedback controller produced by the manufacturer to move the arm to a desired joint angle, but that's it. So this is a policy that takes images and spits out joint angles. That's it. Everything in between is a black box. It's a very big and very complicated black box that's built on top of AI, pre-trained AI models, large language models. But this is like the sci-fi version of robotics, and it's kind of working, right? Okay, so let's understand a little bit more about this VLA phenomenon. So VLA stands for Vision Language Action Model, and it's sort of piggybacking on the Vision Language Model, but ChatGPT is a Vision Language Model, Gemini is a Vision Language Model. These models started as LLMs, and then they graduated to VLMs because they can understand images. And then now the idea is that this is the next progression of moving from the VLM, which is virtual, into the physical embodiment, which is the VLA. So the VLA outputs actions. It outputs robot actions. It doesn't output text. LLMs and VLMs output text, as we all know, right? And so the idea of the Vision Language Action Model is you start with a pre-trained vision language model in the same spirit as Gemini or ChatGPT, but much smaller, about 1/100th the size. And the model that most people use, including the folks at Physical Intelligence, is called PaliGemma. It's an open source model produced by the Gemma group at Google Research, and there are many different flavors fine-tuned for different things. The PaliGemma model is in particular good at visual question and answering. And this is a total Google product. It has no intrinsic connection to robotics. It's just meant for public use, right? So Pi takes PaliGemma, and then they further train PaliGemma with specific robotics data, examples of robots carrying out tasks like folding your laundry. And then you get the performance that I just showed you in that video. There's a lot of nuance here, and we'll get more into the nuance. So this architecture the best example being Pi Zero was first introduced in this paper by Black. This is the paper from the Physical Intelligence Company in late 2024. So the history of the evolution of VLAs goes back to 2023, really. So this team in Google Robotics, as I mentioned, they have RT1 and RT2. This is Robot Transformer 1, Robot Transformer 2. RT1 was not, it wasn't piggybacking on a pre-trained language model. It was just a custom model. So this was not really a VLA properly, but it kind of laid the groundwork. Palmy was also not a VLA because it did not output language, did not output robot actions directly. It outputted text in the form of instructions for a robot to carry out. It was very much like ChatGPT. And then RT2 was the first one that basically took Palmy and took RT1 and stuck them together and made the first VLA. All this work happened behind closed doors. Nothing was open sourced. The scientific research community had to just sit and watch and wonder what the heck was going on. But the papers were published, but basically we had to take it on faith. Then in 2024, the scientific team behind these works started publishing open source works, Octo, OpenX embodiment, Open Cross embodiment, which is a large data set of robotics, robot manipulation data set from across many labs all around the world. And with this paper, they also released a model trained on the data called RTX, Robot Transformer X for cross embodiment, and then OpenVLA. OpenVLA has probably become the most well-known model that's out there in the public domain from the research community. And this work in particular was the best paper award winner in ICRA in 2024. These works, by the way, have all amassed probably by now 1,000 citations, I'm guessing, in 2 years. These are major turning point papers in robotics, right? I don't know of any paper in robotics that's amassed 1,000 citations in 2 years until these papers in 20. These are like, we're talking a pivot for the trajectory of robotics. Punchline, though, unfortunately, if anybody of you has ever used these models, they don't actually work very well. They're super overfit, and it's hard to get them to perform in a research lab. So the team that developed all these models went out and started Pi, and then produced these models Pi 0 and Pi 0.5. Pi 0.5 is still the latest and greatest VLA that's in the public domain. And these actually work well. We use them in my lab all the time. If you stick to the procedures the way they're intended to be used, they're really quite impressive. And then NVIDIA, the Gear group in NVIDIA produced Groot, which is their kind of answer to Pi. It's also quite effective. To my knowledge, these three models are the ones that really work in practice. And if you want to get into this research, that's what I recommend using. Okay, so I talked about physical intelligence. This was, from my perspective, kind of the flagship company that grew up out of the VLA concepts. But there are many other companies that have grown up, and some are even much more valuable than physical intelligence. So physical intelligence, I think, is 2 years old, and it's valuated nearly $6 billion. It's raised over $1 billion in cash. Skilled AI, also developing the same kind of model technology, it's valued at over $14 billion. Dyna is a recent upstart. It's a company that is famous for folding T-shirts. They have a robot that can fold T-shirts continuously and has done so in live demos for like an hour, just never making a mistake. Nearly $1 billion valuation. These companies are all investing in the technology of VLAs, right? So enormous amounts of capital pouring into this. Rhoda and World Labs are kind of adjacent. They're not exactly VLAs, but they're kind of quite similar. Also high valuations. And then you have the robot, the companies that build robots, the hardware, and are also investing in VLA models to drive that hardware. Figure is the flagship, $40 billion valuation, crazy. You guys have seen the Figure humanoid, right? And there's a number of others. This is only a subset. So there's just an enormous movement of capital flowing into this idea and the robots that are going to benefit from this idea. Okay, so surely, with all of this investment and tremendous scientific interest as measured by the citations, surely somebody has managed to measure whether or not generalist policies like VLAs actually generalize. No, they haven't actually. So they're starting to. So I'll talk about our work in this area, and I'll talk about 3 other papers that are currently under review. This is brand new work, it's unpublished. All the papers that try to measure the generalization capabilities of VLAs, to my knowledge, are still under review from the scientific community. There are papers that are released by the companies themselves that say, look at how wonderful our product generalizes, but can you trust that, right? These are press releases. So no, in our studies, these models do not generalize. I'm going to, of course, give much more nuance to these claims. These models rely on a technology called the output head, which is the thing responsible for producing the robot actions, the low-level actions that move the joints of the robot around. And so it's worth digging, and that's what makes that a VLA versus a VLM, right? So it's worth digging into the action head and asking, do the action heads actually generalize in the action space? Or do they just memorize the training action chunks, so to speak, the sequences of joint angles? They just memorize the sequences of joint angles. There's virtually zero generalization or interpolation in the action chunks in the current state of technology. Do VLAs memorize latent token embeddings? If you go further, deeper into the architecture and look at the transformer, which is the VLM, and all the tokens as they flow through the transformer, are those patterns of tokens memorized? There's a high degree of memorization, something like 90% of the volume of the tokens that flow through these trained models are fully memorized from the training set. So it's a tremendous amount of memorization going on. Is this bad? It seems kind of bad. I mean, certainly this is a little bit contrary to the narrative that has made VLAs seem so attractive. Are we stuck? Is there no way forward? I would say no. I don't want this talk to be a downer. I want this talk to be an upper. Because you guys, as scientific researchers sitting here, not as Google employees or as Pi employees, you're looking for problems to solve. And if Pi comes along and says we solved all the problems, robotics is done, we're out of a job, right? So my message is we're not out of a job. There's a lot of good science to be done. Okay, what can we do about it? Well, the practices that we use to make these models work in our labs, this is called fine-tuning. It's part of the standard procedure involved with these models. I'll talk more about it later. It's the current practice is very blunt and not very nuanced, and there are much better ways to do fine-tuning, and I'll talk about a few. We have no good analytical tools to understand how well our models are trained as they're being trained and after they're trained. The only methodology we have in hand at the moment is you train the model, which may take days and cost a lot of money, and then you deploy it on your robot, and you keep deploying it and then you measure the statistics. How often does it fail? And if it fails 50% of the time, you train it again with different data. It's this very expensive, very slow trial and error loop. We need diagnostics that allow us to say at training time, oh boy, things are not working out. We need to do something different. Okay, I'll talk about some examples of how to do that. At the end of the day, we need better training data. We need larger volumes and more diversity in our training data in robotics. So the largest open source resource in training data is the OXE dataset, which I described earlier, open cross embodiment. And it's just tiny peanuts compared to large language model training data sets and vision language model training sets. So we need more data, more diversity, and we need to be able to learn from a greater diversity of types of data. And then finally, I'm going to talk a little bit about something I call metacognition. Sounds heady, sounds abstract, and it is. Metacognition is something that humans and most mammals do as part of controlling our bodies. It's thinking about thinking. It's understanding the limitations of our capabilities, what we can and can't do. It's knowing if we're doing a good job in the moment, and it's using these resources to improve over time. I do something, oh, I didn't do a good job. I'm going to do it a little bit differently the next time and a little differently the next time, and that's how we learn and improve through experience. Maybe it comes as a surprise to some of you. Maybe it's old news to many of you. Robots do not learn through experience. In fact, LLMs and VLMs do not learn from experience. The machine learning model is that you learn from the engineer at training time from data. You freeze the weights, you deploy. Those models at deployment time are frozen, just like any software. They're versioned and they're frozen. They don't learn online as you interact with them, and robots are the same way. So how do we get to learning through experience? So then I'll close with are VLAs the answer? Well, they're not the answer. They're part of the answer. They're very interesting technology. They're the first step on a journey towards generalist robot policies. They're the beginning, not the end. And that's good news for us. So I'm going to go through a very brief sort of review of VLA practices and architectures, how they're used and how they're built, and how they're trained. So VLAs are trained through imitation learning. In fact, all of the most performant real-world robot autonomies learning-based robot autonomies in the past 3 years have been trained through imitation learning. This might come as a surprise to some of you, or maybe it's old news to many of you, but this is not reinforcement learning, right? In robot learning, you have reinforcement learning, you have imitation learning. Reinforcement learning has been the main focus of robot learning for the past 2 decades, at least, maybe 15 years, I don't know. Intensive research, tremendous volumes of work, tremendous amount of nuance and complexity in reinforcement learning algorithms. Punchline, at the moment, for these kinds of problems, for training a policy where you command with language and you carry out the feedback loop with vision, reinforcement learning doesn't work. It's not to say it won't ever work, but right now, this is not the tool that works. Imitation learning works. Imitation learning is older and simpler than RL. It's very simple. It's this. You sit down a person to teleoperate your robot. That person then drives the robot hand through some teleop interface to pick up the thing and put it over here. You ask the person to do that 50 times. You record the images and the actions, the actions that the person used to produce that motion and the images the robot observed while they produced that motion. And that's a training data set, just a standard old-fashioned supervised training data set. So then you train a policy, which is just a machine learning model that maps from images to actions, using the images as the conditioning data and the action as the label. It's old-fashioned machine learning. That's how these things are trained. There's no reward function. There's no notion of task inherently in these robots. The task is implicit in the data itself. And if there are language labels, then it's implicit in the language labels. And there's no simulator. The training is done entirely in the wild with real robots and real people producing the data. Okay. So this is basically what I just described. You have a teleoperator, you collect the data, that data is a data set, you use that to train your neural network, which represents the policy, and then you deploy the policy. And specifically, the data is images, usually from multiple camera views simultaneously. The standard setup is you have a wrist-mounted camera that looks at the high-detailed physics going on at the grasp point, and then you have a third-person view camera to look at the whole scene. So you usually have 2 cameras, sometimes 3. And then you have actions, which are the labels for machine learning. And the actions are nowadays action chunks, which means they're a short horizon of 16 actions or 20 actions that the robot is intended to apply in sequence. So we label it AT, but AT is actually a vector looking forward like 16 time steps into the future. That's what the data looks like. And then the policy is a feedback policy, and it's important to recognize the limitations of these feedback policies. They map directly from image to action. There's no history. There's no memory. There's no integrator, so to speak. They're not PID controllers. If anything, they're only PD controllers. They're very complicated nonlinear things, but they're just PD controllers. That's a rough analogy, right? What I'm trying to convey is that there's no memory in these policies. So if I train a policy to put a little red ball in a box and close the lid, and then I ask the policy, if I could, I don't know how I would, ask the policy, is there a red ball in the box? The policy would have no idea, has no idea what it just did. Okay. But still very powerful. So together with these advances and, in using imitation learning to train policies and also the practical performance of these policies, there has grown up a sort of standard machine interface for collecting the data to train these policies. These are called, workstations, where these are teleop workstations where you have 2 robot arms that are active and then you have 2 robot arms that are passive. You can see the passive robot arms. There, you can see this guy is driving the passive ones. He moves them around, and then that moves the active ones just like puppets. There are little triggers on the passive arms to fire the grippers. And it's if you've ever played with one of these things, we have one in my lab, and they're all over the place in these tech companies. They're quite immersive. They're kind of fun. It's like a little video game, and you can actually get quite a lot done as the human operator in terms of teleop tasks. So here's the sort of dirty secret, maybe not dirty secret, but maybe the strange, let's say, operating model for these multi-billion-dollar companies, virtually all of them that I know of that are out there sort of promoting this vision. What they're really doing and what they're really using their billions of dollars for is to hire robot operators to sit in warehouses like this and teleop. Seriously, there's a new economy in Shenzhen, China, and also in certain places in the US, where we have farms of workers that sit in these teleop workstations, and those workstations are just milking people for their data, which that data is then going to be used to train robots. And so you have these warehouses where 3 times a day, 8-hour shifts, people rotate and just come in and sit down just like a factory. And then they see a little task screen. It says fold 30 t-shirts. Fold the t-shirts, check, 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 check. Okay, put away 10 dishes. Put away 10 dishes. And then they clock out. They're done with their 8 hours and they go home. And that's the new economy that's growing up around these companies. It's very strange, if you ask me. But that's the model to scale data. We'll do this long enough, we'll get enough data, and then we'll have the chat GPT moment where our robots become conscious. You can hear the skepticism in my voice, right? But this is generally the operational model. Okay, so let's talk a little bit about the policy architectures. So the VLA is basically a combination of two older policy concepts that were not generalists, they were specialists. They were meant to be policies to do one thing, and they were meant to be trained on a small amount of data for doing that one thing, like picking up my water bottle and putting it over here. And these policies are called the ACT, Action Chunking Transformer Policy, and the DP, the Diffusion Policy. They came out in the same year at the same conference, RSS 2023. And both of these papers are cited, I think, 1,400 times, something like that. Extremely influential papers. And 2023, I mean, that was less than 3 years ago. But this now feels like ancient history. Like we've very strongly moved on from this. But we've learned two lessons from these policies. One is how effective imitation learning is for building robot policies, and the other is how to train robot policies using modern architectures. So the ACT, which was from Chelsea Finn's lab, uses the transformer architecture, very small transformer without any language tokenization, just the continuous value tokens that reflect actions. And this, the key to this thing was to auto-regressively predict action chunks. It worked very well. And then the diffusion policy basically repurposed the common architecture concept for image generation from AI, right? You have AI image generators where you type in some text and then the model just hallucinates an image that is described by the text. And the way those work is through a diffusion denoising process. Not going to go into too much detail, but basically you start with a random sample of noise for your image, and the model is trained to iteratively denoise by regressing on itself through multiple steps to eventually create an image, and that image is now a hallucinated image that looks similar to the training images but different. And so in this paper, which was from Sharon Song's group and also in collaboration with TRI and Russ Tedrake's group at TRI, they repurposed this to do the same trick but with actions. So you start with randomly sampled actions and then you iteratively denoise. The trick is exactly how you train the denoising filter, but you iteratively denoise until you get like a coherent, sensible action plan for the robot. And both of these were super effective, and they were kind of like watershed breakout moments, but they just solved that one task, right? They were not language enabled. You couldn't command with language what you wanted them to do, and they just would do that one thing. Okay, so then basically those lessons were incorporated into this VLA concept. So basically you have this action head, which is a combination of a transformer and iterative denoising. So basically, it's a transformer that starts with random tokens, which represent actions, and then it denoises to get something that looks a little bit more like sensible actions, and then continually auto-regresses on itself until you get your final set of actions, and that's the action chunk. But then it's conditioned on this pre-trained backbone, as I mentioned before, PalyGemma. The pre-trained backbone is something like 3 billion parameters. The action export is 300 million parameters. So these are, they sound like large models. They're in the low numbers of billions of parameters. But for comparison, Gemini and ChatGPT are about 1 trillion parameters, low trillions. So these are about 100 times smaller. And they need to be because they need to operate in real time and closed loop to close a feedback loop, right? So these can run on a powerful 4090 GPU desktop. They can run at something like 5 hertz, roughly, something like that. That's the speed for one inference. Okay, so these models are trained in multiple phases of pre-training and then a final phase of fine-tuning. This is the standard recipe for foundation models. This is how your language models are trained, your VLMs are trained. Other like Dino and Clip, these are how these are trained. So basically, the Gemini team at Google pre-trains a language model on language tasks and pre-trains this thing called a VIT, a vision encoder. Their model is called SIGLIP, stands for Sigmoidal Language Image Pre-training. The vision transformer basically tokenizes images, takes an image, splits it into little patches, and then turns those patches into tokens, and those tokens live in the same token space as the language tokens. So this allows the backbone, the language backbone, to reason about the content of the images in the same semantic way that it reasons about language with tokens. So this then, these two pieces are pre-trained, and then they're stuck together and further pre-trained, and this is all done by Google, the Gemma team, and this produces PaliGemma, which is the vision language model that's open sourced. And then this goes to Pi, just like Pi takes this model just as any of us could take the model because it's open source, and they further pre-train this architecture on robot data, a large mixture that includes the OpenX embodiment as well as a bunch of in-house data that they don't release to us. And then this is the final pre-trained Pi model, which they release open source to us. And then we further fine-tune it with this practice called supervised fine-tuning, where we take our particular visuals, our particular task, our particular robot embodiment, and we kind of lock in the model to be effective for that particular scenario. And this is the standard practice. Okay, so now we're going to fly through, so we've kind of leveled up on the state of the art. We're going to fly through some recent results from my lab. These are all, two are unpublished results, and one is a paper that's going to be presented at ICRA. I think it's being presented this week, actually, if I'm not mistaken, at ICRA. Okay, so firstly, do VLAs generalize after supervised fine-tuning? So when I say after supervised fine-tuning, this is really important because we have these many phases. The model changes hands through many teams and many different data sources in pre-training, and then you have this little cap on the top, which is supervised fine-tuning, which makes the robot work in your scenario. After supervised fine-tuning, does that model retain some of the general knowledge that it's experienced through its many phases of pre-training? It doesn't. It's weird. It doesn't. It's like, why are we going through all this trouble? It's not to say it can't, but in current practices, it doesn't. So there have been 4 papers that are all currently on arXiv, including ours, that have documented this independently from independent research groups. 2 from research groups in China, 1 from Sergey Levine's lab. These 2 groups documented the phenomenon that these fine-tuned models don't generalize. Sergey's lab, his student Yadov, who I don't know personally, proposed a remedy called retain. And then this work from my lab by my student Suning Huang proposed a different method for remedying this, and then we compare our method against the one from Sergey's lab. This is quite interesting because Sergey is one of the leader of the movement of VLAs. He started at the VLA movement in Google Robotics and is a co-founder of Pi, and so he's, if anybody is behind the idea of the generalist robot vision and how powerful Pi is, it should be Sergey Levine. But this paper in the abstract says, these models are recently understood to not generalize at all after supervised fine-tuning. Okay, so here's an example of the problem. This is your Pi 0.5, the latest and greatest open source model, fine-tuned on a standard robotics benchmark called Libero. It's all in simulation. I'm going to show you other examples in hardware, but this is in simulation. So after supervised fine-tuning, the supervised fine-tuning data set consists of a bunch of tabletop scenes like this with appropriate objects, and then simple tasks like put this thing there, described by color and location. So here is a task that was seen in fine-tuning. It's a little variation on the task, but the actual prompt was seen in fine-tuning. Pick up the book, put it in the caddy. Hooray, it does it, great. Here is a prompt not seen at fine-tuning. Pick up the mug and put it in the caddy. Oh dear. Oh my goodness. This is a 400 billion parameter model that's been pre-trained on untold volumes of data, and it can't pick up a cup. It has seen this cup in many other tasks with many other scenarios. It knows very well how to pick up cups. But somehow, in supervised fine-tuning, the model has learned to associate the background scenery with the task rather than the language of the task. And so it's getting confused. I mean, this is my anthropomorphization, right? So the background is telling me pick up the book, but the prompt is telling me pick up the cup. What do I do? And then it freaks out. Here's another example. Supervised fine-tuning. Put the white cup on the right plate. Put the yellow cup on the left plate. It does great. So this is a variation, a holdout example from one of the fine-tuning tasks. Okay, great. Put the white cup on the left plate. Left plate. I said left plate. No, it's putting it on the right plate. Put the yellow cup on the right plate. No, it's going to ignore left and right because, again, it's getting confused. So we call these two different species of generalization failure. One of them we call concept lock-in, where it takes the context of the scene and uses that as an encoding for the task rather than the language. And then spatial lock-in, where the fine-tuning examples have a certain bias directionally, and we can't overcome that bias with a new prompt. So you can see in the attention, in looking at attention maps averaged over layers throughout the vision language model backbone, what the model is paying attention to in the image. So the original prompt, put the book in the caddy. The model is rightly paying attention to the book. Put the mug in the caddy. The attention is still on the book, with a little bit of shift focus towards the mug, but not enough, right? Okay, so my student Suning saw this and brought it to myself and his co-advisor, my good friend Jeanette Bogue, also working at Stanford. And we said, this isn't right. You didn't do it right. Everybody knows these policies are extremely powerful. They can pick up anything and put it anywhere. And he did it again and again, and he kept coming back with the same results. And then he found these two archive papers from these other groups showing the same result. And so we thought, my goodness, we have a problem, don't we? And so he started researching techniques to overcome this problem, and he started basically messing with the fine-tuning recipe, trying to lock the parameters of there are three different modules. There's the image encoder, there's the language backbone, and there's the action decoder. So he tried locking or regularizing these different modules in different combinations using full supervised fine-tuning, something called low-rank fine-tuning, LoRa fine-tuning. And he found one thing that really works well, which is very simple. Just L2 regularize the weights of the vision encoder, the VIT. The vision encoder is the thing that allows you to combine images with language. It allows the model to know what it means in the image when I say a book. When I say a book, the vision encoder lights up the book. When I say a mug, the vision encoder lights up the mug. So in supervised fine-tuning, basically the weights of the vision encoder were being overwritten to lose their language meaning and to instead become a short circuit from vision to task execution. So you can freeze them, and that helps a little bit, but Suning found that actually if you just regularize them with an L2 penalty like this, so this is the pre-trained weights that we get from Pi, and this is the weights that we supervise fine-tune, that this really helps to break concept lock-in. So simple. The other thing was at the action head to overcome spatial lock-in, right? So if like 90% of your examples always involve putting the mug on the left-hand side of the scene, then it's going to have a really hard time putting on the right-hand side of the scene. And basically what happens is that the action head is basically a vector flow field, right? You start with random actions, and they sort of flow through a vector flow field until they meet the final action chunk. And that vector flow field inherits a strong bias directionally based on supervised fine-tuning. So we remove that bias through something called contrastive prompt guidance. Basically, we influence the vector field at runtime, not at training time. At runtime, we influence the vector field by first taking a vector field that arises from our desired prompt, and then a vector field that arises from one of the training prompts. And we basically take the negative of the training prompt and add it to the positive of the active prompt. And so we're basically saying, do this, but don't do this. And that effectively removes that bias that gets locked in at supervised fine-tuning time. So I'll show you the effect of these. This is the image encoder regularization to break concept lock-in. Okay, so this is with standard supervised fine-tuning, and you can see this is hardware examples. So we're telling it to put the green block on the blue block. You can see it didn't do that. we said put the green block on the blue block. It didn't do that. This is concept lock-in, right? And then you can look at the attention map. The attention is all on the wrong block. It's on the blue block instead of the green block at the beginning of the grasp. This is with our fine-tuning, regularizing the encoder weights. Again, put the green block on the blue block. Cool. So now our 3+ billion parameter model with the entire world of internet pre-training has the spatial intelligence of about a 2-year-old, if we're lucky. Probably a lot worse than a 2-year-old, but at least it can put a green block on a blue block. Okay, and then here's the contrastive prompt guidance. So we're visualizing the effect here. So basically, the rollout as executed after our contrastive prompt guidance, and the prompt is put the left cup into the box. The rollout is in red, and you see it's successfully putting the left cup in the box. Without the contrastive prompt guidance, the flow of the vector field is shown in the green. So without that contrastive prompting, the arm really wants to go to the right cup, but we're preserving the command to go to the left cup. And here's an example that's actually fusing both the VIT regularization and the contrastive prompt guidance. Open the door with the apple. Open the door with the apple. This is with standard supervised fine-tuning. It's doing it wrong, obviously. It's opening the door with the banana. And then here, this is open the door with the apple with our 2 regularization techniques, and it does the right thing. Okay, so that's great. I'm just showing you cherry-picked examples, and really to do science, we need to do it statistically, right? So here's a set of a bunch of tasks from the Libero data set. Again, 3 are examples of concept lock-in, 3 are examples of spatial lock-in, and then 1 is an example of a fusion of the 2, and that's the one with the doors marked with the apple and the banana. This is our model. We don't have a name for it yet. I'm sure we'll come up with a clever acronym. And you can see the success rates. This might not knock your socks off. These are out of 20. 19 out of 20 is pretty good. 11 out of 20, 13 out of 20. I mean, we're not ready to put this in a factory or in grandma's home as a helper yet, right? Clearly. But if you look at the baselines, this is way outperforming the baselines. So I hate to pick on this work from Sergey Levine because the guy is brilliant. He does amazing work. But we did compare against that competing method called retain. And it does better than standard supervised fine-tuning, which would be 0 across the board. But it's still 0 in many cases, but it's getting some successes. And the method in the retain paper, what it does is it does full supervised fine-tuning, and then it takes the fine-tuned weights and takes an average with the pre-trained weights. Literally, just sum them together and divide by 2, just averaging in the weight space. And clearly that does something. We're getting better than 0 performance, but we think we can do a lot better. And then we have another example. We did an example that's fine-tuned on the Droid data set, which is a lot bigger than the Libero data set. And that does pretty well. It does pretty well, especially in these concept lock-in examples. Doesn't do so good in the spatial lock-in examples. And so we're taking this as a hint that the volume of the data set for supervised training is also important. If you start getting into thousands of examples of different tasks with lots of variety, then you can break these lock-in phenomena. Okay, great. So do these models at the action head memorize action chunks? I see that I'm running short on time, so I'm going to have to accelerate a little bit. Right, so we see that supervised fine-tuning somehow erases the benefit of the pre-training, and we've introduced some remedies for that. But now let's look at just the action head. Is the action head capable of emitting action chunks that are generalized beyond the training action chunks? Can we interpolate or extrapolate in action space? We found that the answer is no. So we studied DP policy, which is the predecessor to the action head in the modern VLA. This is work that's going to be presented at ICRA, and you see the authors there, Cheng Yi, Gatti, and Xu. And we started with some anecdotes. So we heard from active researchers in this area. This was about a year and a half ago, so this was all quite new. We heard some funny things. We heard, to make DP policies work well, so we were trying to spin up DP policies in our lab and play with them. To make DP policies work well, you have to overtrain them really bad. So when you're training a model, right, you have the validation loss and the training loss, and typically you look at the validation loss. When that gets minimized, you freeze your weights, you're good to go, because that's the indicator of generalization. If you do that for a DP policy, it will not work. This is well understood. It just flops. It just does random motions. It's very bad. You have to go beyond, deep into overfitting until your training loss gets low and your validation loss is high, and you just ignore the validation loss. And then the DP policy does magic. And this should be very confusing. It was very confusing for us. How can you overfit and generalize at the same time? What's going on? So this was a big red flag that something weird is happening. Then we started investigating, after training, the actual geometry of the action chunks emitted at runtime, right? And we started comparing them with training action chunks, and we started producing the plots that you see here, which visualize inference action chunks, the closest in Euclidean space training action chunk, and the second closest training action chunk. And those inferred action chunks sit right on top of the closest training action chunk with virtually no influence from the second closest training. So they're just emitting memorized action chunks. You basically have a finite library of action options, and you're just choosing. The controller says, I'm going to choose number 1. I'm going to choose number 3. It never chooses 2.5. It can only emit memorized action chunks. It seems. This is just phenomenological, right? This is empirical. So then we devised a similarity score that basically formalizes what I just said. It just takes the Euclidean distance between the emitted action chunk, the inference action chunk, and its closest training action chunk. That's the distance on the top of the fraction, and then normalizes that by the distance between the closest and second closest action chunk. And then we do 1 minus that to make it a similarity. So when the similarity score is 1, you're exactly overlaying the closest. You're exactly overlaying one of the action chunks from training time, right? This does not produce a linear combination. This is not a softmax. So if you see one bar at 1 and another bar at 0.5 and another bar at -10, that's totally acceptable from this score. The score is just meant to show, like, the closer you are to 1, the more you are doing memorizing that action chunk. And then we ran the policy, and this is what we saw. There's one bar that's 1, and all the bars are 0. So again, so we did basically exhaustive exercises in a bunch of different training regimes, and this is what we see. So these models just memorize action chunks. But this is how they behave in closed loop. These are videos from the original paper, which was, again, from RSS 2023 from Sharon Song's lab. Beautiful paper. I'm not knocking the paper. The performance of these policies is unquestioned. It has been validated left and right labs all over the world, including my lab. How can you get this? Look at the robustness here. Somebody can flip up the cup and just put it in a random orientation, and the policy will go and put it in the desired orientation. You can move the pizza around. I'm pointing at my computer as if you guys can see it. You move the pizza around, and the thing will follow the pizza. So there's, like, incredible robustness somehow. And so we hypothesize the following, that diffusion policies memorize an action lookup table. They don't do any action interpolation, and that this is actually the secret to why they perform so well. It's not a bad thing, it's a good thing. Okay, what's going on? Why is that the case? It's because these policies are trained in the low data density regime. In fact, all robot learning is in low data density if you compare it with, like, language model training. The volumes are just tiny, like millionths of the number of training examples, right? Okay, so with that sparsity of data, you don't have enough data to interpolate. If you try to take an average of action chunk 1 and action chunk 2, you get garbage. And so the models that interpolate do poorly, particularly in OOD situations. The models that memorize, at least they're producing a sensible action chunk. You know it's sensible because it came from the labeled training data set. It may not be perfectly appropriate for the scenario, but at least it makes sense in a relatively close scenario. And then through feedback, you're able to switch in this library of action chunks. So it's like a feedback reactive policy with a finite set of skill primitives that you can choose from. And that's how you get the closed loop robustness, is that you're constantly re-choosing your action chunk from your skill library. Okay, and this closed loopness makes things robust. So the reason why the DP policy memorizes is because memorization turns out to be the inductive bias of diffusion models. Diffusion models, again, are typically used to create images, and they've been repurposed to create action chunks. And it turns out that these models in a low data regime this is what they do. They memorize. Not all models memorize. Like the transformer doesn't memorize. The transformer interpolates in low data regime. The DP model memorizes. So this is a simple exercise where we're trying to train a DP model in the data space is just 2D points. And so we're trying to basically learn the distribution of these 2D points which are distributed on the surface of a star. So, so we should be able to recreate a sample, like generate a sample from the surface of this star using DP training. And if we have sparse samples on the star, you can see the DP just memorizes those samples. If we have dense samples on the star, the DP does a good job. And this is basically generalizing to the manifold of the star. This is basically the regime of large vision models, vision generation models that are trained on billions of images. Now you might say, well, why don't you just regularize the model, use a smaller model with fewer weights, or do early stopping, like stop your weights when the validation loss gets low? You interpolate on the wrong manifold if you do this, because you don't have enough data to interpret the right manifold. Okay, so that's the secret. That's what's going on here. So to kind of further test this, I'm running short on time, but we did this quite extensive empirical evaluation of OOD scenarios. So we looked at basically interpolation examples where we asked the model to perform in examples that were very similar to the training examples, but still within the same distribution. Then we did extrapolation examples where we asked it to pick up the cup as we move the cup farther and farther out of the scene. We did more extreme interpolation where we asked it to pick up the cup as we move through kind of a data vacuum in the middle. And then we did visual OOD, so we added distractors, multiple different distractors. We did wild visual OOD, which is conditioned on cats and dogs. Had nothing to do with the training images. And then we did lighting OOD, so we put in harsh lighting that casts shadows. And we compared the diffusion policy, the ACT, the contemporaneous policy action chunking transformer, which was also very influential, and then a foundation model, GROOT, a VLA foundation model from NVIDIA. And we found that the diffusion policy in all these cases, no matter the OOD conditions, still emits one training action chunk. When you condition it on a cat or a dog, it emits a training action chunk. Very confidently, I'm going to do this when I see a cat. And what's interesting is that in the extreme OOD cases, it always emits the same action chunk. So the DP policy actually emergently has like a help me flag, or I don't know what's going on flag. It just puts all that mass onto a particular action chunk. We call it the garbage bin. It kind of reserves an action chunk as a garbage bin, which is interesting. ACT, which is based on a transformer, it does interpolation, which can be good and can be bad. So in completely OOD scenarios, ACT starts drawing from all the action chunks at once and produces very erratic behavior that sometimes can be unsafe. So the diffusion policy inherits a certain safety because you know it's not going to do anything wild because it can only draw from the training chunks, right? Whereas ACT is not the case. It can be very erratic. And then GROOT behaves very similarly to the diffusion policy, but it actually is way more stable under OOD scenarios. So the GROOT is this pinkish bars, and the GROOT signature looks more or less the same across all the OOD scenarios. So it's harder to fool GROOT and to get it to do funny things in the OOD regime. Okay, and then finally we did a final experiment. We said, well, if diffusion policy is really just executing a lookup table to find action chunks, let's just do that. So we trained a policy called the ALT policy, action lookup table, where we encode images and then we look at the distance in the image encoding space between the encoded image and the nearest training image, and then we just emit that associated action chunk associated with the training image, the training action chunk. It's way smaller. It's like less than 1/10 the size or even 100th the size of the diffusion policy, and it's way faster. So the diffusion policy is quite slow. It runs at about 2 hertz on a large 4090 GPU. Our policy runs at 100 hertz on a GPU. It's really dumb. It's not meant to be a smart policy. It's meant to be a very dumb policy. But it basically, I don't have the video here, it turns out, but it performs identically to the DP policy. You really can't tell the difference, except for it's way faster and requires much less computation. Okay, great. I see I'm really late on time, so I'm going to really speed up. Okay, So of super recent work, so now we see that there's a lot of memorization through supervised fine-tuning. There's a lot of memorization in the action output head. We wanted to see if there was also memorization in all of the different latent layers in the language model, right? And so we pulled this tool from large language model analysis called a sparse autoencoder. And it's a diagnostic tool that has basically given rise to a field called mechanistic interpretability for LLMs, where you can basically take large industrial scale LLMs and find out like the main concepts that they're aware of, and you can also steer them in the space of concepts. So there's a really cool paper, I think it's on the next page, this paper where a team from Anthropic took what's their primetime model? What's Anthropic's primetime model? Quint? Say it again? Claude, thank you. So they take Claude and they make Claude think that it's the Golden Gate Bridge. So they take the concept of Golden Gate Bridge, which they discover through a sparse autoencoder, and then they just pump it up. Whenever that concept comes through the token flow, they just hit it by like a 10 times gain. And then everything Claude says is about the Golden Gate Bridge. You ask anything, it's like, well, if I were the Golden Gate Bridge, I would tell you to solve your math problem like this. So it's very interesting. So we use this tool. It's basically a scope that you stick into what's called a residual stream in your large language model, and it allows you to take the tokens, all the tokens that flow in mass through that stream at that point in the residual stream, and allows you to basically train a small finite basis representation for that stream. So you basically take your continuous valued tokens and you pull out instead a finite set of discrete valued tokens that with the goal that at every point in time a very small number of these discrete valued tokens are fired in response to all these continuous value tokens, and these are the concepts or the features. So we trained this thing for a VLA, and then we trained it. I think we trained it for Pi0 and for OpenVLA. After supervised fine-tuning on various data sets. And then we categorize those features as either memorized or generalizable. And the memorized ones we characterize as being the features that only activate on specific training examples, right? Like training example number 3 for picking and placing my water bottle, that feature only lights up then. Versus generalized features which light up across a lot of different training examples, a lot of different tasks, and should correspond to generic skills, right? And so what we found, I'm going to go forward. What we found is that for Pi 0.5, the latest and greatest, fine-tuned on the Libero dataset, 98% of the tokens at this particular layer of the PaliGemma model are memorized. They only light up on one training example. 97% if you average across a whole bunch of different points where you put your scope in the flow. The Droid dataset, which is a lot larger and a lot more diverse, 95% roughly are memorized, or if you average across multiple layers, it's about 90%. So 2 things to take home here. Yes, we're doing a ton of memorization all throughout the model, front to back, right? But it seems that as the data sets get bigger and bigger, we're doing less memorizing and more generalizing. So that's at least a sign of hope. And then OpenVLA, which is this model that came out a little bit before the Pi models, this just almost fully memorizes everything. So this maybe explains why people have a hard time using this model. Okay, great. So I'm going to move forward and look at what can we do. So I already talked about changing fine-tuning practices. I talked about developing better diagnostics. That's this sparse autoencoder tool that I described. So I'm going to talk also just in 2 minutes about getting more diverse training data and incorporating metacognition concepts into our models. So one road to getting more diverse training data is to use, let's say, world models or world simulators to step in for human collected training data. Human collected training data takes a long time. It's a lot of human effort, a lot of expense, a lot of infrastructure because you need the teleop rig. And it's variable quality because the human gets fatigued and humans have different skill level at teleoperating the robot. And so these are main challenges, right? So if we have instead a simulator that doesn't look like, PiBullet and doesn't look like Isaac gym, but instead looks like the real world. It needs to look like the real world to be able to fool the visual motor policy into thinking it's the real world. So we have simulators like this, then maybe we can use data from those simulators to augment the training data, and then we have greater diversity and greater volume, and we can train more general policies. So we tested this idea in a recent project. It's called Pie. I like to call it Pie in the Sky. It turns out there was apparently some marketing issues with this. It was in collaboration with the physical intelligence, the company Pi, and they said, we can't call it pie in the sky because of whatever. Some lawyers said no, so we're going to call it pie but make it fly. But I still like pie in the sky. The paper is called Pie but make it fly. It's on archive. And this is work led by my student John. So we took a drone, we put a gripper on the bottom, we took the Pi 0 model, we fine-tuned it with a bunch of human teleop demos of flying through gates and also picking up and dropping off objects. And then we further fine-tuned it with synthetic data in a 3D Gaussian splatting 3D visual simulator. And here's examples of that. This is synthetic data of the gripper flying around. This is the gripper view. This is a third-person view. So it looks somewhat realistic. I guess it depends on what your tolerance is for realism. In places it looks realistic. It can, if you have a really high-quality 3D Gaussian splatting model, look very realistic. But it's not. This was not piloted data. It's totally synthetic data. And it looks like I removed the results slides. Oh, okay. So here is an example of that model with that fine-tuning recipe going through a long horizon task. So it's picking up some chips. It's going to drop the chips in the bin. It's going to navigate some obstacles. It's going to pick up a sandwich. It's going to fly back, and it's going to drop the sandwich off at the table. This is all in response to a text prompt. So what we're actually showcasing here is the ability to do language composition. The model was only trained on little subtasks in that sequence, and then we prompted it at runtime with the composition task, and it's able to achieve that task. It still does a lot of overfitting, I'll be honest. But we're slowly making strides towards generalization. And then finally, metacognition, and then I'll wrap up because I know I'm late. What is metacognition? It's something that we all do naturally. It's thinking about our activities, the limitations of what we can do, and how well we've done in the past, which ultimately goes into our own online retraining capabilities. We get better through practice. Robots do not get better through practice, right? And so my student Chen Zhang wrote this paper, developed this method, which is called SARM. It's going to be presented at ICRA. It's being presented this week, I believe, which is a very simple idea. It's a task progress model. And there are actually multiple task progress models out there. This isn't the only one, but this was reaching state-of-the-art performance, leading the pack. And basically, it's a model that is trained on the same task training data as your policy. And the job of this model is to tell the robot where it is in the task on a scale from 1 to 0. 0, I just started. 1, I'm completed. And so the robot can use this as a signal of how well it's doing at the moment. Like, oh, I've been at 0.5 for the past 3 minutes. Something's going wrong. Or I was at 0.5, now I'm at 0.2. I've somehow screwed up, right? And so it's just a tool. It's just one piece in a puzzle that would eventually become metacognition. How well have I done? How can I do better next time? And we're comparing here against a very well-known recent baseline called Rewind. And you can see the ground truth is the dotted line, so we're doing better at tracking task progress for folding t-shirts. Okay, great. So big picture outlook. Things are not as solved as they might appear. And that's good news for everybody in the room. There's a lot of good research to do. We need to expand the data sets that we learn from. We need to learn from human videos. We need to learn from synthetic data sources. We need better world models or world simulators that can help us augment this training data and also help us evaluate our policies. We need spatial and temporal memory. I haven't showed you any examples of robots leaving a room and coming back into a room, or a manipulator turning its head away from the table and going back to the table. That's because those policies don't exist, because these policies have no memory, as I described before. What they see in the scene is all that they know about. If they turn their head away from the bottle, there's no mechanism in the policy to remember there is a bottle there that the robot should go back to. So we need some form of spatial and temporal memory. We need broad context metacognition. What's the task I'm trying to accomplish, and how well have I accomplished that task? How can I improve better in the next time? And all of this should flow into robots that improve through their own experience. Great. TDLDR, current VLAs, cool idea. We're not there yet. They do a whole lot of memorizing, but they're promising signs of how we can make them better and closer to their final goal of a generalist robot policy. And we're not out of a job yet. AI has not taken the job of the humble researcher yet. Although every day it seems a little bit closer, doesn't it? Okay, so of course all of this work is due to my very talented and hardworking students. They're the brains. I just come and talk about what they've done, and then also my wonderful collaborators and postdocs. Okay, thanks. I'm happy to take any questions.
Thank you. Amazing talk. So I think we are a little bit late, so we maybe take at most 2 questions before we get kicked off at the class.
My question is sort of higher level. So, you know, the interesting thing about the scaling era of robotics is that you can draw a lot of parallels with like the history of large language models.
Yeah.
Currently, it seems like we're still at the era of you have to fine-tune VLAs.
Yeah.
Similar to like in GPT-2, that period of time. It seems like a lot of the limitations of VLAs are a result of the need of fine-tuning. Do you think we're ever going to get to a point where it's going to have truly zero-shot capabilities? And if that were to happen, do you think a lot of the limitations and issues are just going to go away with scale?
That's the golden question, definitely. That's the question to ask. Of course, I do not know, and nobody knows. But there are many tens of billions of dollars riding on that. The answer is yes. We just need more data. I'm not fully convinced. I think it matters very much the kind of data. I think the real deficiency in these models is not in vision language grounding. Those two things are well aligned, and we have a lot of volume there. It's in the third point in the triangle, action grounding. Making the association between what I see, what I'm told, and what I do. The do part is what we're missing. And it's really hard to get those labels. Is teleop the answer? I don't know. I mean, there are studies out there. Ken Goldberg at Berkeley has a talk where he goes through the scales and the amount of data, the scales of data involved in VLMs and LLM training versus robot training, and the amount of data we're harvesting right now from people. And he calls it the 100-year gap. He says it's going to take 100 years at the current rate at which we're accelerating to harvest human data to get that volume of data to reach the GPT moment for robotics. That's a very speculative and coarse analysis, but I hope as a researcher there's more than just collecting more data. I'll just say it that way. I hope that that's the case.
Any other questions?
Yeah, I think the last word, swarm, is very interesting.
Oh yeah.
And for metacognition type of model like that, do you think it would be very beneficial if you use it to actually improve your training?
Definitely.
Or there's like another way to use it when you just execute your original learn policy. What's your opinion on that?
So that paper actually does not use this for self-improvement. It's called SARM again, and it uses it for data curation. So we take a large, comparatively large, like maybe thousands of examples of someone folding a t-shirt, multiple data operators folding a t-shirt, and we use that model to score the quality of those human examples. We filter out some proportion, I don't remember, maybe 30%, train on the smaller volume of high quality data, and we get a much more performant policy. So right now, that student, Chanzhong, is working on the next generation of SARM, which is a much more sophisticated model, and trying to close the self-improvement loop. Basically, the model doesn't grade its training data, it grades its own rollouts, picks the good ones, and then retrains. And so we're working on a paper. We actually don't have results yet. We have a lot of negative results. We've tried to there's been a paper from Sergey Levine's lab called, from Pi actually, called Pi 0.6, which Sergey Levine's an author, Chelsea Finn is too, of course, where they announce that they've achieved a self-improvement loop. It's a wonderful company, wonderful researchers, but if you read the paper, there's a lot of human involvement in that self-improvement loop. So you need a human sitting there to babysit the robot to take over teleop midstream, to correct it when it's going off course, and you need a human to label the examples of what's good and what's bad. And then you get self-improvement. So we, of course, would like to automate all that. The robot should be able to manage its own self-improvement cycle, right? We're working on it.
Thank you.
Yeah.
All right, so let's thank our participants.